So up next, ladies and gentlemen, we have a session on the topic AI and safety. I think this is a much needed topic, one much needed topic. And we have our speaker, Mr. L. Ravichandran from aithoughts.org, who's going to present. This gentleman is the founder of aithoughts.org and a leading AI evangelist focused on AI for industry and ethical AI. With over 4 decades of IT leadership across Mahindra, HCL, and Tata Group, he retired as a president and COO of Tech Mahindra and a member of the Mahindra Group Executive Board. He now champions responsible AI adoption, contributing to thought leadership and advisory roles in the industry and academia. Ladies and gentlemen, please join me in welcoming Mr. Ravichandran to join us on stage. Please, sir.
Thank you, good afternoon, and thanks for giving me this opportunity. But I think talking just after Mahesh is going to be tough. It's because he's doing such cool things. But I have two connections to CMI. And one is I was classmate of the Professor Rajiva Karandikar, who was the ex-director of CMI. And we spent few years together in the college. We spent a lot of time in the hostel. Maybe that's the reason CMI called me to actually give a talk. I may have learned something from osmosis. But the second one is most important. I have lost count how many lunches I've had in the CMI canteen. Whenever I used to come to see Rajiva, he will take me to the canteen. And there is a Hindi saying, "Aapka namak kaya." Basically, CMI ka namak kaya. And so when they call me to say, "Can you give a talk?" I have to say yes. But my only hope is, you should not become like Sole. Sardar, aapka namak kaya, aap goli khao. So we have a nice topic there. I think we were discussing with Ramki and he was talking about safety and then Chennai being a manufacturing hub. And just like agentic AI become a big talk. And now the new basically toy for the AI industry is physical AI. And then so there is going to be AI like in a powered units running around. And amidst us, and they can come and harm us. They can come and lift us and put it somewhere. Basically, a robot lifting something in the factory. So, what are the kind of safety mechanisms? And what are the open problems still there in that field? It's something we will just want to quickly take you through. Just 7th, 8th, 9th in Las Vegas, we have this biggest show called CES, the Consumer Electronics Show. And the whole topic on the day one when they launched was physical AI. Everyone was talking about physical AI, where basically actually equipment, robots, machines, they are going to have AI inside. And they are going to be interacting with humans. And NVIDIA, on top of their GPUs and chips, they made a biggest announcement that we are getting into physical AI by launching what they call Alpha Mayo, which is part open source and part owned by NVIDIA. Basically a level 4 autonomous car where people can take the product and they can build cars which can be level 4 autonomous driving. So this was basically saying that it can not only that visual AI, but it can do reasoning and it can do safe driving. And where the Hyundai come and said, we want to become number one in physical AI. We want to take the leadership in physical AI. And if you go to any Hyundai car manufacturing factory, by 2030, that there are going to be 30,000 to 40,000 robots working there. And they are going to be partnering with humans and actually working in collaboration. These are the two biggest announcements actually in the Las Vegas conference, which just concluded yesterday. So obviously physical AI seems to be the basically thing in everybody's mind. And what is physical AI? Basically products which have a physical mass and they have AI built in and they really interact with you and me, interact with the external world, lift things to do assembly, move things around, drive cars, and they use obviously visual kind of sensors, audio, video, and kind of reasoning, etc. Once you start working together, that concept of industrial robots, and they said, no, let's not call them robots, let's call them cobos. And so they collaboratively work with the human. So in a factory, if you have 10 steps to be done for a particular product, kind of sub-assembly, you can do step 1 by human, step 2 by robot, step 3 by human, and they can basically hand over, jointly do things, and basically work like another basically person. And then can they work along with humans, or the early robots were basically, they will not interact with humans, they will just work all alone. And so this is the new concept of cobos which have come in. Same thing on the Industry 4.0, 5.0 initiative. Again, they are talking about human-centric automation, human-robot collaboration, and basically going from all the way from the supply chain, warehouse, stores to production floor, to packing and shipping, and the whole process, how we can basically use AI and automation. Wherever you go, how you can work together in a collaborative way. And then the new factories, what used to be the PNC machines and all the other machines, they are seamlessly integrated with SAP kind of ERP systems. So from the production planning to production scheduling, shift scheduling, and then loading the task to the PNC machines, and then working along with cobos. So the whole basically production floor activities can be made. And then you look at it, human safety becomes the most important thing, because we are going to be working in close proximity with humans, with kind of robots. And so there is going to be the additional factor. Yesterday, there was a panelist talking about responsible AI. So this becomes the responsible robo. And what kind of safety mechanisms we need to put, and how do you make sure those things are optimally done is what is the basic going to be my topic. And all the other kind of panelists and from yesterday we are listening, but we have an AI system which can really harm us. It may not kick you like this picture, but this actually happened in a Tesla floor, and then somebody took a video and put it on the social media, and it became viral and it became a problem. But this picture actually happened, but it was during the testing phase. So it may not harm you, but by mistake you go close by, it may pick, instead of picking apart like it will pick you with the giant class and put it in the bin. And then they ship you, they put it in the truck, in the cargo bag. So human co-workers' safety is obviously the kind of top priority. And of course, the robo to robo, basically multiple robots doing different tasks, and they're clashing with each other. So what are we going to do? And all the expensive PNC machinery in the factory, because the robots going bad and going and dashing against, and an expensive, basic multi-crore machinery in the plant. So there are multiple safety factors. But we'll focus today on the human co-worker safety. And this is the reference paper I have used for the topic, and it's about 2 years old, where they are talking about a dynamic way of doing it. Is because today's standards and the way the robots are manufactured, they can do one thing. They either collaborate with humans or don't collaborate with humans. They do limited number of things, because the certifications and the standard requirements are extremely high. But so, if you have so much of restrictive kind of robots, the level of automation is going to become less. So if you want to increase the level of automation, they have to work together, they have to handle exceptions, they have to handle delays, they have to exchange work in case there is a problem, and say, I do this, you do this, and then we will basically make up for the loss of time, etc. And so they actually come and proposed like a deliberative safety, which is basically like in a dynamic safety mechanism, which robo can choose between multiple safety levels on actual event happening on the basic factory floor. So many of the examples and discussions are from this paper. And it's a very simple thing which basically say robo, he'll actually pick the things and put it in a box and then do a small pre-assembly, and then the box will be transported to the assembly line. And if by mistake robo drops the part, and basically robo will not stop and actually bend to pick it up, because it is that kind of whichever plot is kind of fallen down, like a human will come and pick it up and then put it there. And if there is a delay in the shift, then they can jointly work together and then say, you do something, I do something, and then dynamically plan. So that this is the basic case study. And if you have a very simple kind of problem like this, basically, and how are we going to approach the safety? Is what is the discussion in the paper. So, few things are strategic. Safety through control, basically saying, how can the robo stop? How can the robo basically plan the motion in terms of direction, in terms of speed? And then can it actually do a little bit of prediction? Especially when the humans are coming, how fast are they coming? By the time can I finish my work? When I finish my work, will the human operator be too close to me? And then do a little bit of a prediction. And basic thing is, I don't want any contact with human. Contact avoidance, or detect the contact and try to stop it. So basically these are the kind of mechanisms which the engineers use it when they design the robots. And the standards and everything will basically tell you, look at what are the risks. What is the probability of that occurrence? What is the frequency of that occurrence? What is the potential impact? Is it going to be a small injury, or the human operator will actually die because there is a very heavy duty picking machine? And so they look at it. And then various factors are considered, like you can do a safety monitored stop. And so robot just comes to a stop as quick as possible. But the robot is still on. It can immediately start when the actual human goes away. And there could be other occasions where you just control the speed. We are traveling at 10 kilometers an hour. We just cut it down to 4 kilometers an hour. And then you can actually avoid. So, and then power and kind of force limiting. As soon as a human being comes, how much of force you exert, immediately that comes down. So, by mistake, you put a human also, you're not going to crush the person's neck. But at that time, the kind of robot cannot pick heavy-duty items. It can pick only lightweight items. And so you lose some capability, and the last thing, the hand guiding is actually, there is actual physical contact between the human and the robot, and basically how do we need. And so if there is a hand touching or hand guiding, and then typing something in the robot's keyboard, etc., that basically how do you make those parts softer, basically rubber kind of thing rather than steel, so it doesn't come in contact with humans, etc. And the paper suggests that look at degrees of freedom. How many tasks can the robot do? Only one? Or it's a set of 5 or 10 tasks, and the robot is trained on all 10, and it can pick and choose what is the kind of task it wants to do. And what kind of interaction level you need with the humans. Is it handover? That do you work? And then concurrency is, do you work in the same area? Basically same area in the factory. And then speed. Speed of the robot in terms of moving from place to place. How fast it can go. And these are the 4 parameters which you have to manipulate to come out with the best level of automation. And the robot can select one of the kind of safety measures and then say that I will basically work like that. And if you look at the most restrictive thing where less level of automation is, if I see a human there, even that end of the room, stop. This is like when you see the airport buses. When they see a plane, they stop, because that is their protocol. If they see a plane, they have to stop. So that is called a perimeter safety. So you have a safety perimeter, and if there is any human within the safety perimeter, you should not move. Exactly stand where you are. And the human moves out only, you can move. And then a zone safety is, the basic zone is available for both, but you have to reduce the speed. So by mistake, human comes closer, you will be able to control. And then reactive safety is, you basically work closely with the humans. And speed will be fairly low. And your active safety is where you really understand the human intentions, and you can change trajectory, you can turn, you can actually take multiple paths, but basically making sure that the humans are safe. And there is something called planned safety. If there is a delay in the shift, then it can be, you can actually jointly agree with the robot on, this is what I'm going to pick on this side, you are going to pick on this side of the aisle, and we'll go there and pick for the next 30 minutes. And so both of us can do the picking. And after 30 minutes, you go back to your old job so that we'll be able to catch up on the delay. And it is planned, and then the robo is programmed, dynamically programmed, and the human also knows that the robo is going to pick on the left side, I'll pick on the right side, so basically human is safe. So these are the kind of 5 safety mechanisms. And just an example, for example, picking and placing the parts, you don't need degrees of freedom. Just pick, place. And your zone safety is sufficient. I can pick on lane number 1, and the human can pick on lane number 2. There is no confusion. And degrees of freedom of flow, you can use the zone safety, both are working on. Suppose the robot drops the kind of part, and the human has to pick. Because the human is going to be actually on the way. Because the robot is picking, it's about to put the parts, it dropped. And the person has to go to where the part is dropped and pick it up. And so you have to get into reactive safety mode where the speed has to be low, and then basically humans have to be managed. And if there is a delay in the shift, 2-3 hour delay, and now there is a reprogramming, and so you do planned safety. So both robo and humans agree on what is the new schedule. You do this, you do this, you do this, I do this. And then you program it and then start the work. And kind of pre-assembly, because both of them will be assembling together, close contact. You get into the active safety mode where the speed will be really low. And then once you put the parts into your autonomous vehicle, then speed is the most important thing. Take it to the shop floor. And so it can basically go to the shop floor. And their degree of freedom is low, interaction is low, speed is very high. And so you we actually put some drawings there saying automatic vehicle coming, and so humans don't enter. And so it will be maybe even a small barrier, and where you cannot enter. So just a very simple task where you can get the best level of automation by dynamically programming this deliberative safety mechanism. And a lot of standards are there, but the problem with standards is they are very rigid. And even though there is 25 updates have come in, but they are not really taking care of the active safety, reactive safety, planned safety, and all the reprogrammable kind of things, etc. And the standards need revisions. I will just basically take you through 2 or 3 points and stop. The last time anyone thought about robotics and then working with humans, and robots can really harm humans, almost 80 years ago, Isaac Asimov, in a science fiction book, wrote the 3 laws. A robo may not injure a human being through inaction or allow even another human being to kill. So, do we need a universal robotic law to make sure that as the robots are coming, your human supremacy is there? Why do we need human-looking robots? I was in fact chatting with Professor Karandika's son. He works in Google in UK. And when I asked him the question, he said, same question I have. If for a particular task 10 hands are required, let it come with 10 hands. Or let it come with 10 basic face like Ravana. How does it matter? Because the job is what is important. They can hide, how many legs, how many hands, how many eyes. What is the task at hand? So, we are so confident that we have reached the evolutionary chain, the topmost. This is the only skeletal design which we have to put for robots, or it's a psychological thing. And human stupidity prediction, because they will walk into restricted area looking at mobile, just walk in, fall down, they may fall sick, etc. So if that is so many problems in a controlled factory with robots and even trained operators, what is going to happen to autonomous vehicles where there is only one robo and everything else is all of us like you and me? So these are interesting challenges. And how do you identify who is a human? So do we need a reverse Turing test? So the last slide is, you put 51% weight for human or put 100%? Do you put infinite weight for all the prediction parameters to make sure that kind of at any cost human will be protected? These are the decisions the CEO has to take when they are deploying automated factories. So huge area, a lot of research yet to be done. And then thanks a lot for giving me this opportunity.
Thank you, sir. We open to one question, if at all. People, if you have question, you can probably go ahead. Okay, thank you. You can probably think, and he's all available during the break. You can network with him and sort out your questions as well. Thank you so much for the engaging session, sir. May we request Professor Rajiv sir to join us on stage and felicitate the gentleman with a token of gratitude, please.